Hello everyone, my name is Kirti. Today this is the second lecture of Advanced Discrete Mathematics, Unit 3. In the previous video, we discussed about the graph and basic terminologies of the graph. In this video, we talk about what is simple graph. A graph v, comma e is called a simple graph if G is free from loops and parallel edges. What does it mean? That a graph is said to be simple graph if it doesn't have the loops and parallel edges. Let's see it with an example. There are 1, 2, 3, 4, 5 vertices and 5 edges. But we can see that there is no loop on any vertex and there is no edges. That means no two vertex are same for any edges, because in the parallel edges, if this is vertex x, this is vertex y, then we form edge e1, and similarly we form edge e2. Then e1 and e2 are said to be parallel because their end vertices are same. But here we can see that in this graph there is no parallel edge and no loop, so that's why this is a example of simple graph. I hope you clear with the definition of simple graph. Now move forward with theorem that G be a graph, nm graph, that means n number of vertices, m number of edges graph. Then the part first, degree of V is always twice of the degree of edges. That is, the sum of the degree of all the vertices is twice of the number of edges. क्या कह रहे हैं कि जो डिग्री होगी वर्टेक्स की किसी भी ग्राफ में वो हमेशा एजेस की डिग्री के ट्वाइस होगी. लेट्स सी द प्रूफ. बिफोर seeing the proof, let us take an example. If we have a vertex v1 and vertex v2 and edge e, then e is formed by v1 and v2 like this. This is v1, this is v2, and we form the edge between this. This is v1 and this is v2. Here we can see that one edge is formed in a graph only when there is two vertices, because with one vertices there is a edge which is self loop, and which is in a self loop degree is counted twice. तो डिग्री इसकी क्या हो जाएगी? 2. बट दैट मीन्स एक वर्टेक्स के ऊपर एज बनाएंगे तब भी उसकी डिग्री 2 होगी, और एज बनाने के लिए हमें 2 वर्टेक्स तो चाहिए होती हैं. वी मस्ट नीड 2 वर्टिसेस फॉर फॉर्मिंग एज. सो हेयर वी कैन सी दैट देयर इज 1 edge and 2 vertices. So in this proof we have to prove that V belongs to capital V. Degree of V is equals to the twice of degree of edges. Here this is the degree of vertices, this is the degree of edges. So here we see that one edge formed by 2 vertices. So that means there always be, this proof satisfies that degree of V is equals to 2m. Now let's see the proof. Let G be a nm graph, n number of vertices, m number of edges. Let V, small v, belongs to set of vertices capital V is such that degree of V is not equals to 0. We suppose degree of V is not equals to 0. That means V is not an isolated vertex, because in the isolated vertex the degree of vertex is 0. Okay, so this implies there exists an edge. If the vertex is not isolated, that means it form edges. There exists an edge E belongs to this edge set E such that E formed by 2 vertices V and V1, V dash. Again, if E dash be the another edge in the edge set, then there exist 2 more vertices belongs to vertex set V such that E is formed by X and Y. Now we see that there exists E dash contributes 1 to the degree of X. What does it say? This is X, this is Y, and this is E dash. E dash contributes 1 degree of X because of this edge is equals to 1, and degree of Y because of this edge is equals to 1, because this edge is incident on y and this edge is also incident on x. Thus this implies e dash contributes 1 to the degree of x and 1 to the degree of y. Thus each edge, this we are talking about here only for one edge. Now here, thus each edge, for all edges in the graph in E, edge set E, contributes 2 to the degree of the vertices. One edge always contributes 1 to this side, 1 to this side. That means one edge contributes 2 to the degree of vertices always. So for all edges in E contributes 2 to the degree of vertices in V. Hence the sum of degrees of all the vertices is twice the number of edges, because one edge contributes 2 to the degree of vertices. Or equivalently we says V belongs to vertex set V. Degree of vertex is always twice the degree of edges. And we also see with the example that if these are two vertices and this is one edge, then we can see that E1 is formed by two vertices, here two vertices and one edge. So it both are equal when it is multiplied by 2. So 2m is equals to 2, where m is equals to 1. Okay. Now in the second part of the theorem, what does it say? The number of vertices of odd degree is always even. In the second part, theorem says the number of vertices of odd degree is always even. That means the vertices whose degree is odd, they are even in the number. That means if there are n number of vertices whose degree is odd, then n should be even. Okay, so let's see the proof. Let V1 be the set of vertices in V in which degree of each vertex is even. We pick vertex V1 from the set of vertices V in which the vertex degree is even, and V2 be the set of vertices in which degree of each vertex is odd. That means V1 is the set of vertices in which the degree is even, and V2 be the set in which the degree of vertices is odd. So V can be formed by the union of these two vertices. Then we prove the result above, that summation of V belongs to capital V. Degree of vertex is always twice of the number of edges from above. We discuss is summation V belongs to V1. We split V into V1 and V2 because V1 can be written as V1 union V2. So V belongs to V2, degree of V is equals to twice of M. We substitute it, rearrange it, since the degree of V is even, because degree of V is even when V belongs to V1, because V1 is the set of vertices in which degree of vertex is even. So this is equals to even, and hence this is odd. But we know that when we subtract even minus even, then we will get even number. That means subtraction of two even integer, resultant is always even number. Okay, since any vertex V belongs to V2, this implies degree of V is odd, because in V2 all the vertices are those whose degree is odd. So del degree of V is odd, and the sum of an odd number of odd integer is odd. Therefore the number of elements in V2 must be even, because here we can see that this is the degree of V2 in those vertices whose degree is odd, which is equals to the even. That means degree of odd degree of vertices is always be even in the graph. The number of vertices of odd degree is always even. So I hope you like my lecture, and thank you for watching this video. I hope you like this video, and like, share, subscribe my channel. Thank you so much.